maybe a few calculation. So heat can transfer three different ways: conduction, convection, or convection, and radiation. Let's look at conduction. I don't know if you've ever done that, but sometimes you have a fire going on here. The fire's going, and you want to move these wood inside. You put a piece of wood on top of it to keep the fire going in the fireplace, but the piece of wood falls down, and you grab a metal rod and you hold it, try to move that piece of wood. Well, if you're holding that metal rod inside the fire for a few minutes, what will happen to your hand? You get burned. Why? Because the heat transfers through that metal rod. That's how conduction works. That heat, it heats that end, and the heat will transfer through that all the way through your hand, and you will burn your hand. But what will happen if you were using a piece of wood to move actually that piece of wood in the fire? Probably nothing will happen. Why? Because wood is not a good conductor. Some elements are good conductors, others are not. We call them insulators. Metal is a good conductor. Heat transfers the metal beautifully. That's why cooking pans are made out of metal. So once you heat the bottom, that heat transfers all around the pan. The handle on that pan usually made out of plastic, or the end of it, because plastic is an insulator. The heat doesn't go through it. You don't feel it. So we have conductors and insulators. So heat can transfer by conduction. The amount of heat, like for this example, if you want to know how much heat went from here to here, the equation can be calculated as Q equals, that's the amount of heat, it's K times A times delta T, change in temperature, over L, the length of that rod, times the time you left it there. And what is K? K is known as thermal conductivity. And it changes from object to object. Just to give an example, it's a table here. For silver, it's 417. That's K. For gold, it's 291. For aluminum, it's 217. For wood, look at wood here, 0.1. Water, 0.6. Glass, 0.8. Concrete, 1.3. So let's do one example. We'll do it once with maybe, what do you want to use? Copper, aluminum, steel? What do you want to use for the rod? Which one? Steel, okay. Let's use steel. We're going to use steel, and we'll do it with wood. Let's assume I have this rod. The length of the rod is 1 meter long. The end is round. Diameter equals, I don't know, what should we use? How big you want the diameter to be? Maybe 4 centimeters, a decent sized rod. That's the diameter. So the diameter is 4 centimeters, which means the radius is what? 2 centimeters? Which is 0.02 meters. And I have it in this room right now, sitting right here. It's been sitting the whole night. So the current temperature on that one is 22 degrees. And I take this rod now, and there's a fire here that has a temperature equals the fire temperature. Let's see, what should we have for a temperature? 200 degrees. and I take the rod and I put it into the fire and let it sit for a few minutes for, I don't know, how long you want to put it there? 5 minutes? Let it sit there. Well, this is going to heat up. The amount of heat transfer, Q, is going to equal to K times area times the change in T over L times the time. The time has to be in second. So let's look at that. K for, we said what are we using here? I forgot. Steel, was it?
Yeah.
So K for steel is 66.9. Times the area, which is pi r squared. Pi r is what? 0.02 squared. Times the change in temperature, which is final minus the initial. Well, if this is 200 degrees and you put that rod in it for a while, that rod will be also 200 degrees. So it went from 22 to 200. What is the change in temperature? 200 minus the 22. Over the length, which is 1, that's what the length is, times the time. How many seconds did you leave it there? 5 times 60, which is what? 300 seconds. I keep forgetting to turn the thing on. If I push all the right buttons, it says here 4489 joules. Now remember, if I grab that rod in my hand, my temperature in my hand, outside of my hand, it's probably the room temperature, maybe warmer than room temperature, maybe 25 degrees. This is going to be what? 200 degrees? That heat's going to go from that rod to my body. That's why you get burned. We have a change in temperature. Heat going to transfer from the rod to my hand. Now replace that with wood. Same story. So now it's the same thing, but instead of steel, it's going to be wood. And the length is 1 meter. Radius is 2 centimeters, which is 0.02 meters. Final temperature, the same thing. The fire here is 200 degrees. Initial temperature was what? 22 degrees. I'm not changing anything, except instead of steel, I'm using wood. Let's see what Q is. Q equals K times A times change in temperature over the length of it times the time. K. K for wood. Let me look at the chart. 0.1. Area pi r squared. Times the change in temperature, 200 minus 22 over 1, and times the time, which is what, 300? Ready for that? 6.7 joules. That's it. 6.7 joule versus 4,489 joules. If you use, I don't know if we have plastic here. Where's plastic? Do we have plastic here? Ice, concrete, glass, water, asbestos. We don't want asbestos here. Wood. I don't have plastic. But if you look at most cooking pans, they have plastic, or if it's steel, stainless steel alloy, which is only 16.3. Instead of having aluminum, which is 217, this is 16.3. It gets hot, but not as hot as that one. So that's how conduction works. Now another example here is windows. We'll talk about windows. I mentioned that yesterday in the lab. I said if you look at old homes, the windows used to be made out of single layer of glass there. And when it's cold outside, you get up in the morning to look and the windows froze. You see ice on the inside. Now the window actually made out of 2 layers of glass with air between them. Why? Because air is a wonderful insulator. Notice what K for air. We thought actually wood is good. Look at wood. 0.1. Look at air. 0.0234. 0.02. So that's why we have a glass, air, then a glass to make the window. And the temperature could be minus 50 below zero outside. The first layer of the glass will feel it. The inside of that will feel it, but not the outside, because now they get the air between them. Then the second layer of glass will not even see that because the air will insulate that. So let's take one layer of glass. So we have a window that has a 1 meter by 1 meter. This is the window, made out of glass. And let's assume the thickness of the glass thickness, glass is 0.5 centimeter thick. How much heat is lost? That's the question. How much heat is lost? Now we have to give you some numbers. Let's assume the temperature on the outside, we're talking in the air outside, is 0 degrees Celsius. And the temperature inside the house, you have it set up at 21 degrees Celsius. The question again, where is it? How much heat is lost in 1 day? We'll give you some time. In 1 day. So the amount of heat loss, Q, equals K times area times delta T over L times the time squared. I mean the time, not the time squared. And K for glass, let me look and see what's K for the glass. 0.84. What's the area of this window? That's rectangular shape. Length times width. That's 1. What is the change in temperature? Is it 21 degrees the difference? What's the length of the glass? Because you get a picture of the glass. The heat is going through that glass there. As the heat transfer, the glass has a thickness of 0.5 centimeter, which is what? 0.005 meters. And how long? 1 day. Well, how many seconds in 1 day? The 1 day has how many hours? 24. Each hour has how many minutes? 60. Each minute has how many seconds? 60. Again, you picture the glass like this. The heat transfers from this end to that end, so it's traveling through the glass, only the thickness of the glass. Let's see what that number is. 0.84, turn it on again, 0.84 times 1 times 21 divided by 0.005 times 24 times 3600. 304819200. Roughly what? 3.05 times 10 to the power 1, 2, 3, 4, 5, 6, 7, 8 joules per day we lost. That's how much heat. One window. One window. Imagine if you have 10 windows. That's a lot of energy lost. That's why you don't see that many houses with just single layer of glass anymore. You see them in garages, but garages are not heated. And if you have one, you better go dump it and buy one, 2 layers of glass. Get a 2-pane glass there. So that's how conduction works. The other way you can actually heat transfer through convection. You hear a big thing about convection ovens now. Everyone wants to have them. Huh?
I want to be in that math class.
Oh, this one? I think that's pre-algebra.
Yes.
Yep. Convection, convection, you see that where? You see that at the beach more often, you know? How does it work? Let's take the day, during the day or at night. During the day, the sun is out, and you get the land here. You get the ocean here. I should have made the land like red color. Sand here, hot. And you get the ocean here. The water, the ocean. Could be a lake there. Well, during the day when the sun is out, heating that, the land actually will have a higher temperature. Since heat rises, what's going to happen? This heat will start to rise, going up there. And as that heat rises, what's going to happen here, the water? This air will travel this way, try to replace that heat that just left there. So you get that constant breeze there working all the time during the day. At night here, the reverse happens. This is the land. This is the ocean, the water. But at night, actually, the water is warmer than the land. So the heat will rise here. What happens? It pulls the air from the land. And that's the pattern that you see there constantly. So that's why if you live next to the water or on the beach there, you always got a breeze there. If you look Aruba, if you type in Aruba right now, you say, what's the weather in Aruba? Always 85 degrees and breezy. Bermuda, always 80, 85 degrees and breezy. Because a lot of logic there. It's water, surrounded by water. During the day, The sand is warmer, hotter. It's gonna rise. It's gonna pull the water from the ocean, cooler water. Because the temperature of the water, the ocean, what, 72 degrees maybe in Aruba, maybe, or 68 degrees. The land might be 80 degrees, so it's going to travel this way. At night, that temperature might drop to 45, while the water, or 50. The water is not going to go to 50. 68, it might be what, 67 degrees at night? It's a big ocean there. So this is going to be warmer than the land. So this is going to rise, it's going to pull the air in that direction. And again, constantly getting a nice breeze there. That's how convection works, actually. And the last one is radiation. The last form of heat transfer is radiation. I don't have any equations for the other one. For radiation, there is one, but I'm not even going to put it there. But I'm going to have a picture to show you. Sometimes you see a picture. Let's see if this book has it. For radiation, no, it doesn't look like it has it. Maybe a different book might have it. Let's see if I can find a picture. Oh, I don't have it. You see that sometimes people walking, you can see actually the heat coming off their body on a hot day. Or if you look at the track, the railroad track, you can see that heat rising. That's really what that radiation is. I don't have a picture of it. Some physics book have a picture of a guy walking. It's like sweaty and everything, but you see actually like mist around him. And that's how you lose the heat, through radiation there. It says the energy radiated by an object is in the form of electromagnetic waves. I don't have a picture of anything to show you. I wish I have it, but that's how you lose energy. Radiation, you lose energy, or energy radiated by an object is in the form of electromagnetic waves. Now, I might be able to see it maybe in the other chapters when we talk about electromagnetic waves. Let's see if this book has it. That doesn't go that far, this book. I don't have it in this book, no. If anyone, I might have the full-blown book. Can I see chapter 25 in the book?
Sure.
There might be a picture there about some of these waves. Thank you. There's always a person walking. You can see they always show that picture. And the wave is coming off his head, his body. Let's see if I can find that picture. No. I'll look for another book. I usually have a second book when I'm looking at it, but I don't have it with me. If it's really hot like this, I know next week it's supposed to be in the 90s, 95. Just look at an object, like especially a metal object. Look at it, you'll see, like you almost can see some waves coming out of that object, radiation. And that's the form, the third form. Because you can't see most of the waves. Like when you go for X-ray, you can't see that wave coming through you. You know? Some of the waves are not visible to us. A lot of it not visible to us. But the heat ones, you can actually see some of the heat leaving some, especially with somebody who's been hitchhiking for a while. in the hot weather, you see them walking, you get to see that coming off their head, steam coming off their head almost, you know? And that's the third form of heat transfer. Conduction, convection, radiation. There's an equation for radiation. We're not going to cover it here. For those people really fascinated by the equation, I can put it there. The radiation power, P, the net power is equal to E times sigma times A, the area, times T to the fourth. And we've got to figure out what sigma is, and sigma is 5.67 times 10 to the negative 8. There'll be no homework or anything on that, but for those people interested in that, that's what's going to be the equation. This is actually called StefanBoltzmann Law for I think it's a Z with Boltzmann, yeah. I don't know what nationality that name is. Law sounds maybe German. For radiated power. That's what this law is. Yeah. We can do an example on it. That's all right. You got my attention here. Polar bear, the crazy people who go and dig a hole in the ice. They jump in it winter time. They go, it's good for the body. They do it on New Year's Eve or New Year's Day. You won't get me there, but they go and they dig a hole in the ice and they jump in it and they come out screaming. So let's see what happened. First, we need to know what the area of the person is. So we're going to take a person here, a person with area equals 1.15 meters squared. Now, surface temperature. Ooh. What do you want to use for temperature? The example they're using here, minus 30 degrees Celsius. Freezing cold. So temperature in Celsius is minus 30. To convert that to Kelvin, we add 273. Or can't be minus. The temperature in the water may be minus. But the person itself, what's a human body? Was it 98? So what is that roughly? 98 minus the 32. Anyone knows what that temperature in Celsius divided by 9 times the 5? 36 degrees Celsius. Well, you're not going to be, the outside is not going to be the same as the inside. So let's use, I don't know. When is 25 degrees? 28 degrees? You have a temperature on the outside of your body, 20. Take your clothes off, and you're going to jump in the water. You have a temperature right now is 28. If you sit for a while, you're going to freeze. So in Kelvin, that'll be what? 273 plus 28. What's that? 301 degree Kelvin. Now, let's pick a temperature for the outside. You're going to jump in water, right? You're going to jump, how cold the water? Into Well, notice the water. Just think about the water in the ocean. They dig a hole in the ice and they jump in the water. Well, what's the temperature of that water?
Freezing.
Which is what?
Technically 32 degrees.
Or Celsius?
0.
At 0 degrees Celsius. It has to be 0 degrees. Why? Because you have ice on the top. If the temperature above 0, that ice will melt. So he's going to jump into 0 degree water, so that's in Kelvin, 273 degree. And you're only going to jump in it for how much?
10 seconds.
For a short time. Yeah, you jump and you scream out and you get out and you run quickly. The other thing is, we need to know you jump the whole, you're gonna dunk your whole body? So you're gonna jump the whole body? Or you're gonna leave your head out?
Depends how crazy you are.
Okay, so we'll go, you're gonna jump. Go on it, go for it. So let's find what P equal to. P is equal to E times sigma times the area times the change in temperature to the 4th degree. And change, the way we write the change in temperature is actually that you're going to write it as the final temperature minus the surrounding temperature. So we're going to write that instead of the difference, T to the 4th minus the surrounding temperature to the 4th degree. Now let's see what's going to happen. You want your entire body submerged? What portion? E, that's the portion, that's 1. All of it. You're going to dunk your head and everything. What is sigma? 5.67 times 10 to the negative 8. What is the area of the person? How big that person, the surface area exposed to that cold weather? I think I said 1.15.
Yes.
Times T4 minus surrounding TS. The temperature of the person, which is what? 301 to the 4th degree minus the surrounding temperature, which is the frozen water or the ice water there. 0, which is in Celsius, that's in Kelvin, what? 273? To the 4th. You do the math. 301 to the 4th power minus 273 to the 4th power. You multiply that by 1.15. You multiply that by 5.67 times 10 to the negative 8. $173. 173. Now we're talking about power. That's joules per second. This is watts. Every second you're going to lose 173 joules when you jump in. So if you try to stay there for 5 minutes, good luck. 173 times 5 times 60. You lost 51,915 joules. You are froze. I forgot what the longest you can stay in water, because I watched Deadliest Catch. They say if they can't get that person out in about 3 to 4 minutes, he's done. Your system shuts down. Because you can see the number that you're going to lose.
There must be a constant for how much energy expended if you're in frozen water a human can do before shut it down.
We're gonna be losing that heat, and your body's gonna try to send the blood to the vital organs, you know?
It's very patient, it's very individual.
Yep.
There's no constant.
So that's really how radiation works, but